Okay, so in this lesson, we are going to return to the idea of using tree diagrams. Before we use tree diagrams to look at the possible combinations of outcomes in some situations, we're going to take that a step further and we're going to use tree diagrams today to help us calculate the probability of different outcomes, especially when those outcomes are dependent on each other. So in this first example, we're going to select 2 balls from a jar, one at a time without replacement. There are 5 balls in the jar, 2 that are red and 3 that are blue. And we want to find the probability of all of the possible outcomes. So what we're going to do is we're going to use a tree diagram to break down each of those outcomes. So to begin with, I'm going to draw 1 ball from the bag. And when I draw, I'm either going to get a blue or I'm going to get a red. Then I'm going to do a second draw from the bag. And again, regardless of whether or not I got a blue or a red, on my second draw, I could get a blue or I could get a red. So all of my possible outcomes, I could have a blue and then another blue. I could have a blue on my first draw and then a red. I could have a red on my first draw and then a blue, or I could have a red on my first draw and a red on my second draw. So those are the outcomes, but now what we're wanting to do is we're going to go back and we're going to find the probability of each of those outcomes. So what is the probability of getting a blue on the first and second draw? What is the probability of getting a blue on the first draw and a red on the second draw? What is the probability of getting a red on the first draw and a blue on the second draw? And what is the probability of getting a red on both the first and the second draw? So what I'm going to do is I'm going to go back and I'm going to look at each of these outcomes. So for my first draw, it tells me that there's 5 balls in the jar. I have 2 that are red and 3 that are blue. So on my first draw, there is a 3 out of 5 chance that I'll draw blue. And there is a 2 out of 5 chance that I'll draw red. Or if we change that to a decimal, 0.6 chance of getting blue and a 0.4 chance of getting red on my first draw. Now my outcomes for my second draw, their likeliness depend on what I've drawn on the first draw. These are dependent events. For example, if I've drawn a blue ball on the first draw, then that means that I have not only fewer blue draws to select, but fewer balls overall. So if my first draw was blue, then that means that now I have 2 blue balls left in the bag out of a total of 4, which would be 0.5. If I'm looking at the red balls that are left in the bag, if I didn't draw a red ball on the first one, then I still have the 2 that were in there left out of 4. So I also have a 50% chance of drawing a red ball on the second draw. So now if I look at my red, if I drew a red ball on the first draw, that means that now there are 3 blue balls left out of 4 balls total. So now I have a 75% chance of drawing a blue. But if I drew a red ball on the first one, then that means that I only have 1 red ball left out of 4 total. So my chance of drawing a red ball has gone down now to 25%. So then if I want to calculate the probability of each of these outcomes, a blue and then a blue and then a red and then a blue, a red and then a red, then I can apply that the idea of these events all being independent of each other. So the probability of getting a blue on the first one is 0.6 times the probability of getting a blue on the second one now is 0.5. which gives me a probability of 0.3 or 30% chance of drawing a blue ball on the first and the second. The probability of getting a blue ball and then a red ball will be that 0.6% chance of blue on the first and then 0.5% chance of red on the second, meaning I also have a 30% chance of getting a blue and then a red. If I look here, the probability of drawing a red on the first draw is 0.4 times the probability of drawing a blue on the second draw is 0.75. 0.4 times 0.75 also gives me 0.3. So again, 30% chance of getting a red ball and then a blue ball. And then finally, my last possible outcome is a red on the first and a red on the second. Well, I have a 0.4% chance of a red on the first. And if I drew a red on the first draw, now I have a 0.25% chance of drawing a red on the second, which gives me an overall probability of 0.1 or 10% for drawing a red ball and then another red ball. Notice that all four of these outcomes represent my entire sample space. And if I take the probability of each of these possible outcomes and add them together, I'm going to get 1. I'm going to get that 100% because either this happens, or this happens, or this happens, or this happens. So their total would give me that 100% of all of the possible outcomes. Okay. In the next example, they want to know what is the probability that a high school athlete will go on to professional sports. They're calling event A the event that the student competes in college, and event B the event that the student will compete professionally. Then they've told us the probability of event A is 0.05. The probability of event B given A, so the probability that the student goes on to compete professionally given that they played in college, is 0.017. And the probability of B given A complement, or given not A, the probability that they compete professionally given that they didn't compete in college, is only 0.0001. So again, I'm going to start with a tree diagram to represent the outcomes. We have a student athlete. And if that student athlete played in high school, then one of two things is going to happen. He's either going to go on to play in college, event A, or he's not going to go on to play in college, A complement. If the student does play in college, then one of two things will happen afterwards. He'll either play professionally, event B, or he won't play professionally, B complement, not B. If he doesn't play in college, again, he could still play professionally, B, or he might not play professionally, B complement. So I'm going to go back and put in some probabilities. They told us that the probability that A happens is 0.05, 5% of student athletes play in college, which means that not A would be 1 minus that 0.05, or 0.95. Then they've told us the probability that B happens given that A happens. So the probability that if A happened, B will also happen. So now we're on this branch of our tree. They tell us that that is 0.017, which means that the probability of B not happening if A has happened would be 1 minus 0.017, or 0.983. They've also told us that the probability of B happening given that A didn't happen is 0.0001. So the probability of B happening given that A also didn't happen would be 1 minus 0.0001, 0.9999. The question wants to know, what is the probability that a high school student athlete goes on to professional sports? And so we can see that there's actually two pathways that the student can take. The student could play in college and then play professionally and end up in professional sports here. Or they could not play in college, but still go on to play professionally, ending here. These two routes we're not really interested in, because in both of these routes, that would be the probability the student didn't go on to play professionally. So we have two possibilities. We're looking for the probability that the student plays in college and plays professionally. And we're looking for the probability that the student doesn't play in college, but still somehow manages to play professionally. So the probability that the student would play in college and then go on to play professionally would be 0.05 times 0.017, which gives us a probability of only 0.00085. The probability that the student doesn't play in college but still goes on professionally would be that 0.95% that they don't play in college times that 0.0001% chance that if they didn't play in college, they go on to play professionally, which gives us an even smaller probability, 0.000095. So we have two routes. They either play in college and play professionally, or they don't play in college and play professionally. These two events are disjoint from each other. So if we want to find just the probability that a student will play professionally, the probability of B, then it's one of those two things. Either they did play in college and play professionally, or they didn't play in college and still play professionally. So the probability that they will end up playing professionally is 0.00085 plus 0.000095, which means that regardless of whether or not the student plays in college, their chance of playing professionally is 0.000945. So I want to take a minute to look at what this would look like if we hadn't approached it using a tree diagram. If we had gone back to our formulas for conditional probability, we still could have calculated this probability, but it would have been a little bit more complicated. So I'm just going to recopy some of that information that they've given us. They've told us that the probability of A, that the student plays in college, 0.05. The probability of B given A, that they play professionally given that they played in college, is 0.017. And the probability that they play professionally given that they didn't play in college is only 0.0001. Well, if I go back to my conditional probability formulas, I'm going to start with this B given A. The probability of B given A is the probability of both A and B divided by the probability of A. Well, I know that the probability of B given A is 0.017. I don't know the probability of A and B. But I do know that the probability of A is 0.05. So if I multiply both sides by 0.05, then I get that the probability of A and B happening, playing in college and playing professionally, is 0.00085. And if you look back at your tree diagram, that's exactly what we calculated for the probability of A and B. And we calculated it in the same way. We took the probability of A and multiplied it times the probability of B given A to get that probability. So this is the exact process we were using with the tree diagram, but the tree diagram actually gave us a visual so that we could see what we were doing. Likewise, if I use my conditional probability formula, the probability of B given not A, or A complement, would be the probability of not A, or A complement, and B, divided by the probability of not A, or A complement. I know that the probability of B given not A is 0.0001. So the probability of A complement and B divided by the probability of not A would be 1 minus the probability of A, 0.05. We get 0.0001 equals the probability of not A and B divided by 0.95, And so if I multiply both sides by 0.95, I get, again, that the probability of not A and B is 0.0000095. And again, I ended up with the same thing here. I had the probability of not A times the probability of B given not A gave me the probability of not A and B happening. And so just like before, if I wanted the probability of B, I would add those probabilities together. It's the probability of A and not B. Either we went on to play professionally and we played in college, or we went on to play professionally and we didn't play in college. Those are the only two possible routes. So 0.00085 plus 0.0000095 gives us the same probability that we calculated before, 0.000945. So whether we use the tree diagram or our formulas for conditional probability, we'll get the same results. It's just that in some cases, having that tree diagram as a visual to follow what all of the possible outcomes are may make the calculations a little bit less complicated than just going with the formulas. But you can use either method and you should still get the same results.